Download this code from codegive.com, link in the description below. OK, let's dive into the world of measurement error as presented in Statistical Rethinking 2022, Lecture 17. This is a crucial topic because in the real world, data is rarely, if ever, perfectly accurate. Ignoring measurement error can lead to biased estimates and incorrect inferences. This tutorial will cover the theoretical concepts, the potential problems caused by measurement error, and, most importantly, how to model it using Bayesian methods. We'll use Rethinking and brms in R for the coding examples. Understanding measurement error. What is it? Measurement error refers to the difference between the observed value of a variable and its true, underlying value. This difference can arise from various sources, including instrument limitations, scales that aren't perfectly calibrated, questionnaires with ambiguous wording, human error, misreading instruments, entering data incorrectly, subjective judgments, sampling variability, the sample used doesn't perfectly reflect the entire population's true values. Definition, the true value doesn't perfectly match what we're measuring. For example, IQ is a proxy for underlying intelligence, not a direct measurement. Types of measurement error, classical error, random error. This is the most common type discussed. It assumes that the errors are random, normally distributed, and have a mean of 0. In other words, some observations will overestimate the true value, and others will underestimate it, but on average, the errors cancel out. Systematic error, bias. This is a consistent error in the same direction. For instance, a scale that consistently adds 1 kilogram to the weight is a systematic error. Systematic errors are more challenging to deal with because they don't average out and can lead to severely biased estimates. Differential error, the error depends on the value of another variable. For example, people might overestimate their height more when they are talking to someone they perceive as more attractive. Non-classical error, this kind of error includes any error structure more complex than classical error. Why is it a problem? Measurement error introduces noise into the data, which has several important consequences. Attenuation, parameter estimates are pulled towards 0. This is especially problematic in regression models, where the coefficients for variables with measurement error will be underestimated. This leads to biased estimates of the effects. Inflated standard errors, the variability in the data will be higher, increasing standard errors and widening confidence intervals. It becomes harder to reject the null hypothesis, leading to type 2 errors, false negatives. Spurious correlations, measurement error in two independent variables can create an apparent correlation between them. Model misspecification, if you don't account for measurement error in your model, the assumptions of the model, example normally distributed residuals, may be violated, which affects any inference drawn. 2. Mathematical representation. Let's formalize the concept of measurement error with some math. Suppose we have a true, unobserved variable x. We observe x_obs, which is a noisy version of x. In the classical measurement error model, where error is assumed to be normally distributed with a mean of 0 and a standard deviation of sigma_error. Error normal, 0, sigma_error. The key challenge is that we typically don't know x or sigma_error. We need to estimate them using our data and a statistical model. 3. Bayesian modeling of measurement error. Bayesian methods offer a flexible and powerful approach to handling measurement error. The core idea is to treat the true, unobserved, values as parameters in the model and estimate them along with the other parameters of interest. Asterisk general strategy asterisk. 1. Define a generative model asterisk. Specify how the data, including the observed values, are generated from the true values and other parameters. 2. Assign priors asterisk. Define prior distributions for all parameters, including the true values and the error standard deviation. 3. Sample from the posterior asterisk. Use Markov chain Monte Carlo, MCMC, to sample from the posterior distribution of the parameters, which gives you a range of plausible values for the true values and other quantities of interest. Asterisk example, simple linear regression with measurement error in the predictor. Let's consider a scenario where we want to model the relationship between a predictor variable x and an outcome variable y, but we know that our measurement of x is subject to error. Asterisk generative model asterisk. Asterisk y normal, mu, sigma, outcome variable. Asterisk mu equals alpha plus beta asterisk x, linear model relating x to the mean of y. Asterisk x underscore obs normal, x, sigma underscore error, observed value of x with error. Where asterisk y is the outcome variable. Asterisk x is the true, unobserved, predictor variable. Asterisk x underscore obs is the observed predictor variable, subject to error. Asterisk alpha and beta are the intercept and slope of the linear relationship. Asterisk sigma is the standard deviation of the outcome variable. Asterisk sigma underscore error is the standard deviation of the measurement error in the predictor. Asterisk priors asterisk. Asterisk alpha normal, 0, 1, prior for the intercept. Asterisk beta normal, 0, 1, prior for the slope. Asterisk sigma exponential, 1, prior for the standard deviation of the outcome. Asterisk sigma underscore error exponential, 1, prior for the standard deviation of the measurement error. Asterisk x normal, 0, 1, prior for the true value of x. For any x underscore obs, there will be a corresponding unobserved x. 4. Code example, using Rethinking and brms. Here's how we can implement this model in R using the Rethinking and brms packages. First, let's generate some simulated data with measurement error. Now, let's fit the model in Rethinking. Key points about the Rethinking code. Asterisk map is a handy function in Rethinking for estimating parameters by optimizing the posterior. Asterisk we specify the model using a list, defining the likelihood and prior distributions. Asterisk we use dnorm for normal distributions and dexp for exponential distributions. Asterisk the most important part is the specification of the x dnorm, 0, 1, true x prior, and x underscore obs dnorm, x, sigma underscore error, measurement error likelihood. This links the observed value x underscore obs to the true value x. This introduces a new latent variable x. Asterisk we use the start equals list, x equals x underscore obs, argument to provide initial values for the x parameter. This helps the optimization algorithm converge more quickly. Now, let's fit the model in brms. Key points about the brms code. Asterisk brm is the main function in brms for fitting Bayesian models using stan. Asterisk we specify the formula as ya plus b asterisk x plus normal, 0, 1, where x is the latent variable representing the true x value. This is the crucial part that tells brms to estimate the true x. Asterisk we define priors using the prior function. Note the class equals b to specify the prior for the slope coefficient and class equals intercept for the prior on the intercept. Asterisk normal, 0, 1, is not an error. The code declares that x is also a normally distributed parameter. Now, let's compare the estimates to the true values. You'll see that the estimates from the measurement error models, both Rethinking and BRMS, are much closer to the true values of alpha and beta than the estimates from a simple linear regression that ignores measurement error. In this example, you will observe the parameter estimates from m_error_rethinking and m_error_brms will be very close to the values declared in the data simulation step. The important considerations and extensions. Knowing sigma_error in the above example, we estimate sigma_error. Sometimes, you might have a good estimate of the measurement error standard deviation from other sources, example validation studies. In that case, you can fix sigma_error to its known value rather than estimating it. This is a strong constraint and will improve estimate accuracy. This can be done by setting sigma_error as a data variable that doesn't get updated. Measurement error in multiple predictors. The same principles can be extended to models with multiple predictors, each with its own measurement error. The complexity increases with the number of predictors. Non-normal errors. If you have reason to believe that the measurement errors are not normally distributed, example skewed or heavy-tailed, you can use different distributional assumptions in your model. For example, you could use a t-distribution for the error term. Nonlinear models. Measurement error can also be incorporated into nonlinear models, such as logistic regression or hierarchical models. The basic idea remains the same: treat the true values as parameters and define a likelihood function that links the observed values to the true values. Model identification. Measurement error models can sometimes be difficult to identify, especially when you have limited data. This means that the posterior distribution might be very wide, indicating considerable uncertainty about the parameter values. Carefully consider your prior distributions and the information available in your data. Stronger priors for x or sigma_error can help. Calibration. Before adjusting the outcome variable to account for measurement error, make sure the measurement tool is calibrated with respect to known standards. Sensitivity analysis. It's crucial to perform sensitivity analyses to assess how your results change under different assumptions about the measurement error. For example, you could try different prior distributions for sigma_error or explore models with different distributional assumptions for the error term. Causal inference. When measurement error is present in causal inference settings, special care must be taken to ensure that causal effects are correctly estimated. Consider using techniques like instrumental variables or front door adjustment to address confounding and measurement error simultaneously. 6. When to worry about measurement error. While measurement error is a pervasive issue, it's not always necessary to explicitly model it. Here are some guidelines. High measurement error. If you have good reason to believe that the measurement error is substantial relative to the signal, i.e., the true variation in the variable, then it's important to address it. This is especially true if you're concerned about attenuation bias. Consequences of bias. If even a small amount of bias in your estimates could lead to important conclusions, example in policy decisions or clinical trials, then it's worth considering measurement error. Availability of information. If you have auxiliary information about the measurement error, example from validation studies, then it's easier and more reliable to model it. Exploratory analysis. Even if you're not sure whether measurement error is a major problem, it can be informative to fit a model that accounts for it and compare the results to a simpler model that ignores it. This can help you assess the potential impact of measurement error on your conclusions. 7. Conclusion. Measurement error is a common and often overlooked issue in statistical modeling. By using Bayesian methods, you can explicitly model the measurement error process and obtain more accurate estimates of the parameters of interest. Remember to carefully consider your priors, assess model identification, and perform sensitivity analyses to ensure that your results are robust. While modeling measurement error can add complexity to your analysis, it can also lead to more reliable and informative conclusions, particularly when the measurement error is substantial. The techniques presented here are a starting point for addressing measurement error in a variety of statistical models.